Hi guys, Shavik here. Welcome back to our YouTube channel. So I know it's too long that we are not meet, but yeah. So I actually busy in some like puja celebrations of my hometown. I went and after that like I come back by last couple of week back only, and then involve in some like priority activity. So yeah, so after Diwali is over and all the festival season is over and we are back to the business. So yeah, now onwards we will cover rest of the parts of the DSA practice sheets that we have prepared, and along with we have decided that system design things we will eventually start. So I actually done some little bit preparations on that part also. I was occupied with that also. So uh, we will start very soon on that also, on system design things also. So yeah, with that note, I think you guys is already aware of with the headlines and the titles of today's agenda. So on today's agenda we'll majorly focus on uh, graph things only. So I think we now if we can go to our sheet. So I think we have a bunch of like very decent problems, I have to say, to practice for this. So we will cover that. So let's see like how many problems we can cover by these sessions, as per the time permit. So we will cover like as many problems as we can, but majorly the fundamental things we definitely have to cover. The templates that I am generally follow for any of the graph problems that I will share to all of you guys, and along with the every lines and every iterations of the meaning of the templates, I will give you a vivid line by line intuitions, and along with the use cases of every lines behind whatever we write over there. I will explain like the fundamentals of every steps, every line by line intuitions I will give you. Yeah, so you'll not do any rush. We will not to rush to cover all the problems, but we'll see like as per you guys will going to digest the things as per the speed. We will cover as many problems as we can. Yes, sounds good, right? Okay, so with this, let's start on this. I just wait for 1 to 2 minutes hardly to basically get a confirmations from you guys, and to allow to join more peoples. And also, can you guys just quickly confirm that voice, audio part and video part and screen share, like everything, so you guys are on path, right? You guys are able to see the things and able to hear me properly. Just confirm on these things quickly on the chat. Okay, we got one thumbs up. So give me 2 more minutes, guys. So, mm, Okay, okay, fine. So let's start. So I just give you a very quick overview of what actually graph stands for. So I also like anticipated that if you guys are try to solve this bunch of problems, and if you are on the path of to solve these categories of problems, so for sure, like you should have some basic understanding of graph. uh, I will give you like very high levels overview what actually the graph stands for, and what actually the major differences of a tree and graph, and on high levels what is actually the difference of a linear versus non-linear data structure, right? And and I will also walk you through that things that the template things that we are discussing, the representations of a graph, and along with uh, the basic traversal, and trust me guys, so graph is nothing but a few set of known algorithms. How good you guys can digest, you are on the top of on graph. So graph is nothing but how good you are basically memorize the very popular, very well-known standard algorithms, and on all the problems of graph is actually relied on that only. So I know, like, you all are basically have a like scared of knowing graph and DP, but literally trust me, like graph is not on that difficult problems. If you know the very standard algorithms of the graph, and by solving a good number of problems, you have the fundamentals cleared on the graph, then 99% of the problems of a graph is associated on the template that we are going to discuss. So please focus on the templates that we are going to share with you, and I am giving you the confidence that with that template you are mostly solve 8 plus 80% problems on any topic, like any of the problems of the world with that template only, right? Yeah. So graph is nothing but if you are familiar with, just confirm me guys, you are able to see, right, what I am writing over the screen, right? Sorry, my handwriting I am also not able to understand. Give me 1 minute. Let me just correct the marker. Okay. So so here we have our graph. So we have two data structure on data structure world. We have two categories. The first category is our linear linear data structure, and the second category is our non-linear non-linear data structure. Agree? That you guys are aware of, should that you guys should aware of. So we have two categories, one is the linear and the second one is the non-linear. And inside linear, whatever the data structures we have inside that linear category, inside this linear category we have, give me 1 minute. Yeah, so inside the linear category we have linked list. Why it is not allowing me to write? So inside linear category, we have the first data structure that we have is nothing but a linked linked list, right? Linked list is a linear data structure. Then tell me what else? What else? Inside the linear category, then we have arrays. Arrays is a linear data structure. Then set. This all are this all. Then we have map. This very standard things that we are using. And for non-linear, whatever the things we have, we have tree, one non-linear data structure. Then we have tell me, then the second one and the most important one is, the graph one. We have the next one is graph, right? Now how, what actually the basic difference of linear and non-linear? So linear means, if you see the structure of a linked list, so 1 then connect to 2, then 2 connects to 3, so that is the structure of a very standard linked list. So there is the data structure you can represent in a single sequence. The data structure you can represent in a single forward sequence, right? In a forward sequence, there is no branching at all, right? But on non-linear, now if I'm going to consider what we have in non-linear. So on non-linear, if you can see the tree structure, so from 1, if I'm going to add a node here, let's suppose we have 4. So now 4, we don't have a structured way, we don't have a defined way of movement. We have few set of movements. So from 1, I can either go to 2, I can either go to 4, right? Now I can either go to 5 also. Now there is no there is no defined or predictive movements. I can go from 1, right? So from 1, now I have opportunities. Now I have 3 opportunities. I can either go to 5, I can either go to 4, or I can either go to 2. So if my data structure has branching, so if my data structure has branching of, if my data structure has branching of more than one paths, then it's a non-linear data structure. Then it's a non-linear data structure. Agree, guys? Agree? So this is on high levels the data structure group or categorize is look like. We have for on linear, we have linked list, arrays, set, hash map, whatever the data structure you guys are using day to day activity. And on non-linear, we have tree, graph, then we have, there is a data structure known as trie data structure, which is also non-linear data structure. If you aware of this data structure, trie is also a non-linear data structure, right? Now how tree is different from graph? On graph there can be a cycle, right? But on tree we never have a, never have a cycle. There is no cycle concept in tree. And the number of edges, what is edges? If I am considering 1 and 2 as a node, then the connections between 1 and 2 is termed as, so this one is my edge, this we call as edge, and these things we are going to say it as a node. We are going to say them as a node, right? This is node and this is edge. So these are very fundamental things. I am pretty confident that you guys should be aware, or if you are not, then go to your like uh, books and things that you are going to have to do for your semester purpose. Then you should have a book level definitions, so that you should be aware of the terms of node and ages things. So these are book level terms, and is very standard things that I am assuming, so you guys should be aware before of like try to solve any problems over the graph. So the terminologies is you should have to must have to know about. But don't uh, go to in unmotivations if you are not aware of these terms, because I am going to give you the very high level touch of the terms which are going to use on to solve the problems. I will going to give you that high level touch, right? And this ages, the count of ages in a tree, the count of ages in a tree is always n minus 1. That many ages should have, right? So these are only book level definitions we are just going to go. But on high levels, if a tree has a cycle, then this particular tree is known as a graph. Graph can have cycle. So the very laying things that you should have to know, every graph is not a tree. Every graph is not a tree. So graph means is a tree? No, you can't be predict it, because if that graph has a cycle, then it is not a tree, not a tree. But every tree is definitely a graph. Every tree is definitely a graph. So that is on the theoretical aspects that you guys should have to aware, and you can go to your semester books and all the stuffs, then you will have some more definitions or more terminologies you guys should have to be aware of, right? Yes. So with this note, we start on the graph things. Let's focus on me very take a very strong focus on the graph now. So I think so on high levels you have the understanding on the data structure kingdom. We have two categories. One is the linear, another one is the non-linear, and inside of the linear and non-linear, we have on the linear we have a category of data structure, and on the non-linear we have the category of the data structure, and then we eventually saw how graph is different from a tree. We have tree, and eventually we have evolved to graph. So initially we have linked list, so from linked list we have evolved to tree, and from tree we have then evolved to graph, right? Now inside graph we have couple of categories. One is like directed graph, and second one is the undirected graph. Undirected graph. See guys, there can be more definitions, more theoretical aspect of graph. So I am not going to dive deep on that, like more theoretical aspect I am not going to dive deep, because that is eventually you guys will definitely cover as a part of your uh, semester purpose. I'm just going to give you what the bare minimum things you have to know to solve a product based company levels graph problems. Before solving any product based company level graph problems, or a decent problems of a graph, the bare minimum things that you have to know, I am going to give you the touch of that only. But you guys can very feel free to opt in your semester level preparations. You should have going to get more fundamentals, more definitive, more structural definitions of this graph, but I am going to give you which you must have to do, or if you are just in the preparation phase, these things you can't skip. These fundamentals you have to be very clear with, right? So this is the two branch of directed graph and undirected graph. And if I'm going to give you the like pictorial view of this. So a directed graph, if I have, let's suppose, two nodes, 1 and 2, and if I'm going to define a path between 1 and 2, let's suppose this is my edge or the path, then that should be a direction. I can go from 1 to 2, but from 2 to 1, if there is an edge, then only I am allowed to come from 2 to 1. But if this edge is not there in place, if this edge is not there in place, then it is not allowed. Then it is not allowed. Similarly, take an example of 2 to, same example only, from 1 to 2, and if I am going to represent is as something like this. So this means this is an undirected edge. So the graph which has directed edge is known as directed graph, and the graph which has undirected edge is known as undirected graph. So what is that? What is the main delta of undirected versus directed graph? So if there is an edge between 1 and 2 in an undirected graph, so that means you can, from 1 you can go to 2, and from 2 you can come back to 1, come back to 1. But if that is a directed edge, then from 1 to 2 so you can go for sure, but from 2 to 1 you can't come back, you can't come back. That is not allowed, that is not allowed. So that is the very brute definitions of a graph. That is the very brute definitions of a graph. Agree? Still now following, still now following, all following, right? All following, all, you guys all are following? Any doubt, anything, or we are good to proceed? Sorry, are we good? Sorry, 1 minute guys, I'm just going to come back. Can you guys just quickly confirm the voice is fine, right? Sorry, I was talking on mute initially. Just confirm, you guys are able to hear me, right? Hello, hello, hello. Fine, right? Anyone? Anyone? I'm waiting, guys. Anyone? Any thumbs up? Anything? Just let me know if the voice is clear. Okay, okay, fine. Thank you. Thanks, Ramu. Thanks. Okay. So now we have discussed on the fundamental things. So we have discussed on theoretical aspects. Almost we have covered theoretical aspects. So that things only we have to discuss on the theoretical side. So now with this note, we can discuss the representation of a graph. So next topic is representation. So first we have discussed what is first we have discussed what is type of graph we have discussed. So this part is done. Then the second we are going to discuss is the representation. Representa- Representation. On graph representation, we have two parts. One is the adjacency list, and the second one is the adjacency matrix. I know you guys is already aware of by book fundamental definitions what is adjacency list, what is adjacency matrix, and these things is 99% cases on or most, I am pretty confident on 100% cases we are not going to use this adjacency metric representations of on any of competitive programmings or any kind of problems that is associated of a graph that we have to be faced on an interview. This representations is not going to helpful for any of such use cases, but this is the most important things. So so I am just going to give you an very high levels. If I am going to give you quickly draw a graph from 0 1 to 2 to 3, and then let's suppose from we have 3, and then we have 4, and from 4 from 2 let's suppose we have 5. So if I going to ask you the adjacency matrix and adjacency list representation. So on adjacency matrix, so this is very simple, and it is useless also at the same time. Why I am stating though? Because it is going to take a very high space of every node. We If there is a connections or not, we have to mark it with some identifiers. If I'm going to write it, then it is very clear to you. So whatever the node value we have from 0 to 5, we have 0 1 2 3 4 and 5. So these are the node values, right? These are the node values. Similarly you can write it 0 1 2 3 4 5, right? Now from 0 to 0, do we have any edge? No. Mark it 0. 0 to 1, yes, yes. 1. Then from 0 we don't have any, mark everyone to be 0. From 1 we have 0 3 and 2. From 1 we have 0, then 3 and 2. From 2 we have 1 4 5. From 2 we have 1 4 and 5. Rest all are 0. Rest all are 0. From 3 we have 1 only. From 3 we have 1 only, right? From 3 we have this 1 only. Rest all are 0. Then from 4 we have 2 only. So from 4 we have 0 1 2 we have, and rest all at 0. So you guys are getting, right? So where we have an edge, so from 5 we have two connections. So on 5 we are go to 0 1 2, and we are marking it to be 1, and rest all are 0. So that is the representation of adjacency matrix. So here you can see, right, whether we have an edge or not, we are going to we are going to need that many space. So the space we need for sure is basically an n square space, always. Now if I am going to write the same adjacency list representation of it, so what we are basically doing, we are taking a map kind of data structure, and from this zero, whatever the connecting nodes, whatever the node we have, we are only marking those, not from zero, whatever the node connections we have via direct edge, we are storing only those. So from zero, what we have only one. From one, what we have. From two, what we have. From three, what we have. From four, what we have. From five, what we have. So from one, we have 0, 3, 2. We are only going to store 0, 3 and 2, right? Now from 2, what we have? From 2, we have 1, 4 and 5. We have 1, 4 and 5. From 3, we have 1. From 4, we have 2. From 3, we have 1. From 4, we have 2, right? From 5, we have 2 again. So this representation is the this if I can small it little bit in the entire screen. So this representation is the adjacency list representation, adjacency list, and this is the representations we are going to use a hell lot of the time in all the problems that we are going to solve. Because here you can see, right, we are not going to take a big of n squared space all the time. If there are, if this is a star graph, so star graph means from every node there is a connections of the of other edges, then on that case only it going to take a space of big of n square. But for all other cases, it is bound to going to take a space of less than of big of n square. So this is the ideal representations of a graph, adjacency list representations. Now this representations is going to change very slightly based on the type of the graph. How many type of the graph we have? So the representations part we are discussing, right guys? If you are following, on type part, how many type we have discussed? How many type we have discussed? The first type we have discussed is the undirected. The first type we have discussed is the undirected, and the second type we have the directed. Now if I am going to take a very small graph to represent, let's suppose this is my graph 1 to 2, then from 2 to we have 3, and from 2 we have this 4 also, right? And let's suppose from 4 we have the path to go to 1. So let's suppose this is my directed graph. How we can represent? So we can represent from 1 we have a path of 2 only. From 2 we have a path of 3 and 4 only. And from 3 we have a empty list. We can go from anywhere. And from 4 we have a path of 1 only, right? So this is the adjacency list representations of this graph. If I can make it one page, so this is the representations of this particular graph. If I can draw the same graph in undirected pictorial view, so we have this 4 to 3, then it is going to be a little different. How it is? So from 1 we have, now we can go to 2 and we can go to 4, right? Because it's an undirected edge, so that means we can go and come back. From 2 we have now the liberty of 1, 3, 4, 1, 3 and 4, every other node I can go. Now from 3 we can go to 2 as well. Initially it was empty. Now from 4, I have now two opportunities. One is 2 and another one is the 1. So 1 and 2, 1 and 2, 1 and 2, right? Right? So we have two opportunities. We have two opportunities. Agree, guys? Agree? Still now it's clear. Still now it's clear. So we have discussed, we have discussed the what things we have discussed. We have completed the type of graph and the representation of graph, right? We have covered the type of graph and the representations of the graph. Two things is covered. Now the most important part is the traversal. The most important part is the traversal. Now the point 3 that we have to know is the traversal. Traversal. Still now, guys, are you following, right? We have total of like more than half an hour, and I'm not sure like how many of you guys are following. And if you guys have any doubt, feel free to ask any questions if you have. If you have any doubt, feel free to ask any type of questions if you have, because that is the ideal times that you can that you guys can ask any type of any type of question, right? Because on that we can spend the time of the QA also. Q&A also we can do. If you have any queries, you can just put it on the chat, and we can discuss for sure. Now we are going to start with the next important, and it is the most important. It is the most important part of any graph problem. So that is the traversal. So on traversal, we have two categories. We have two tests. One is the DFS, stands for depth first search. The name is itself explanatory to give you the hints how we have to traverse. So DFS stands for depth first search. Then we have another test of traversal, which is BFS. So that is stands for breadth first search. Breadth first with first search. So the major delta of these two bucket of traversal is the way that you are traversing, that we are traversing, right? Okay, we have a question to optimize and Naukri website. So okay, we have a question from Jeet. So he is asking, can you make one video on how to optimize InstaHire and Naukri website? Okay, fine. Yeah, Jeet, we can definitely take in a considerations that we can make on how we should apply, how we have to make our profiles on different platforms like LinkedIn, InstaHire, or Naukri to get most of the opportunities to be in the plate. I will take a note and definitely create a video over there for these things, right? Okay, so the test it's on depth first search. If I can draw a very small graph, if I have 1 2, then we have 3, and let's suppose we have this 7, then let's suppose 5. So I'm just taking an arbitrary graph. So let's suppose we have this graph. So I'm just going to give you a high level executions of a DFS, and then I will give you my own template how we can basically on code representations, how we have to basically represents, how actually we have to format our templates to basically use a reusable template to basically give accepted for any kind of DFS or BFS based problems. So I'm just going to give you how actually the DFS first work, how actually the BFS first work, then the writing of the code. If you understand the uh, basically the explanations or the guidance, then you should be on the very top of to write the code by on your own. So the main things, the fundamentals, you should be aware of the fundamentals. Your fundamentals should be very clear. So so let's suppose I have to start from some node. So let's suppose this is my source node. This is my source node. And if I am doing DFS, that is depth first search. Depth first search. So if I am going to depth first search, so from 1, I have the have lag on this particular part, then your entire graph series is going to be again on the same path. You are not going to get anything post of that if you are not be very focused on this particular traversal part, because this is the fundamental, this is the backbones of any algorithms that we are going to derive from these algorithms. All are based on the traversal algorithm only. All are based on the traversal algorithm only. So in DFS, we have two flavor. Either we can go to 2 or we can go to 3. So let's suppose we are going to 3. Let's suppose we are going to 3. So how we are basically going? We are basically going via recursion. Recursion. Or a stack. Or a recursion has a inbuilt stack trace, right? Inbuilt stack it is by default is taking. And we need a visited. We need a visited. So visited, why we need? You guys are going to say by yourself only. After going to iterate with the algorithm, you guys going to get why we need a visited, right? So from 1, let's suppose we are going to 3. So from 1, when we are at 1, we are marking this to be visited. We are marking this to be visited of 1 to be true or 1. So that means 1 is visited. And from 1, we are going to go to 3. We are going to go to 3. And when we are 3, so before going to 3, when we are trying to explore, so what are the neighbor of 1? What are the neighbor of 1? Whose are neighbor of 1? Whose are neighbor of 1? The neighbor of 1s are 2 and 3. Let's suppose choose 3. So we are basically first we are basically check if my node 3 is already visited. Nope, it's not visited. So if my visited of 3 is equals to 0, so that means it is not visited. That means it is not visited. So we are going to go to visit it. We are going to go to visit it. So if my recursion, so if I am going to write it on the high levels, how it should be looks like. So you are going to call your recursion to be a source node. So this is your source node, right? So from source node, you are going to call your recursion. You're going to call your recursion. And you are marking this particular node to be visited, right? Visited or node to be visited. And then we are basically looking for to all of its neighbor, for neighbor in graph of node. We are going to look for all of my 1s neighbor. The 1s neighbor is, who are 1s neighbor? 2 and 3. And let's suppose we choose for neighbor in graph of node. When we are iterating to all of its neighbor, we are choosing if this particular neighbor is not visited, is equals to 0, so that means it is not visited. Then we are going to go it, marking it to be, we are calling our helper functions recursively to mark it to be visited, So how then actually it is going to look like? So from 1 we are going to mark this to be visited. Now from 3, what is the opportunity we have? We have to go to 7. And if it is not visited, yes, it's not visited, man. Go on it. So we are on it. From 7, who are the neighbors? 5. So 5 is visited or not? Okay, 5 is also not visited. So we are landing to 5, right? We're landing to 5. Now our recursion is from 5. Do we have any opportunity to visit any other guys? Nope. We don't have. Then our recursion, our this for loop is going to be exhausted, and the call is going to back to the previous caller node from 7. Now our caller back to 7. From 7, do we have anyone's to explore? Nope, nope, nope. All neighbors are visited. Call back to 3. Anyone left? Nope. From 1, next for neighbor loop is iterating. So from 3 parties done. Do we have any unvisited neighbor? Via for loop. Yes, 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 we have to go for it. And it is unvisited. Yes, man, it is also unvisited. So go for it. So we are on 2. From 2, do we have any opportunity? Any unvisited that we can explore? Yes, we have 4. Again, we are going to 4. So you saw, right? Our way of traversal to be in a particular node, very depth. From 1, we are go to 3. From 3 to 7. From 7 to 5. To extreme depth. To extreme depth. The path that I am highlighting repeatedly. This is the extreme depth. So that's why it is known as depth first search. We are going to extreme depth. We are going to extreme depth. Again from 1. When we started to explore 2, we are going to go to extreme depth. We are going to go to extreme depth. Extreme depth. So that's the reasons this algorithm is known as depth first search. Now, what is the use case of this visited? Just I am going to tweak this graph. Rather than it's a directed graph, I am going to mark it to be undirected, right? So let's suppose it's an undirected graph. So there is no direction at all. So when, let's suppose, if I can quickly redraw it, so from 1 we have 2, there is no actually direction. Then we have 4, then we have 3, then we have 7, then we have 5. So when we are doing the DFS for 3, you are going to go to 7. So from 7, you are going to go to 5. Now, what the neighbor of 5? 5 ka neighbor 7 also. 5 ka neighbor 7 also, because it's an undirected. So from 5, you can again come back to 7. And from 7, you can again go to 5. And from 5, you can again go to 7. So this is creating a infinite. This is going to create an infinite loop. You are traversing. You are basically visiting a group of node infinitely. You are visiting a group of node infinitely. So to avoid this, when we are first visiting, when we are doing the first visiting, first landing a node, we are also going to mark it to be visited. So that means we are not going to, when we are trying to land that particular node, we are not allowed to land. We are not allowed to land because we have already visited. We have already done the visitations of that particular node, right? We have already done the visitations of that particular node. Agree? We all are on the same path, right, guys? So we have completed the DFS on high levels. We have wrote our pseudocode, but don't worry, I will do the exact low level code also. We will compile our code. I will post that, share the template also. So don't worry, on the high levels I have give you the gist how actually the DFS is looking like, looks like, right? It's clear, right? Till this we are good, right? We have covered one of the most important algorithms, that is DFS. Just quickly give a thumbs up on the chat if you are understood till this point. Then you are on the next levels, because you have covered one of the most difficult graph traversal algorithms. We have only 2 flavors and you are successfully able to understand 1 flavor. So just going quickly give a thumbs up on the chat, and please like, guys, please provide a thumbs up on the stream itself. Please provide a thumbs up on the stream itself. We have a good decent audience, but you guys don't provide a like. So please don't hesitate to provide a like. That is going to motivate myself also. So please hit a like. Okay, okay, nice, nice. Okay, fine. Till now things are clear. Everything you are able to understand. I am assuming so. There is no confusions, nothing is there, right? I am assuming. Clear, right? Okay, okay, fine, fine. Okay, so let's move forward. Let's move forward. Now we have the second test. Now we have the second test. So don't basically going to make yourself busy to the other stuffs, because if you are going to make yourself busy with some other task, parallel task, that if you are doing on now time, then you are going to lose the entire, you are basically lost your entire time off to watch this series. So please be focused until we cover these two traversal algorithms. Post that on problem solving, you guys, we are basically iterate the problems, we both, we all are going to iterate the problems in the same go, and I will give you some time to basically try by on your own. On that times you can utilize that time to basically try by your own, or basically involve yourself some other activity. But please don't do basically involve yourself to any other side activity, because these two traversal, if you are not making your fundamentals to be strong, then the entire graph playlist, I have to say, is going to be is a complete big zero for you. So this two traversal algorithms is the backbone or the foundations of 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 any graph problems. So DFS we just now covered, then we are moving to BFS. So now again let me draw the same graph very quickly. Let me draw the same graph. So what we have on this, if I can project it properly, the same graph, or whatever the graph, I'm not going to focus on that. So let's suppose from 1 we have 2, from 2 we have 3, then from here we have 5, then 5 to 4, then 4 to, let's suppose, 7. So this is our graph. Let's suppose this is our graph. So on DFS, you saw we are going to an extreme depth. We are going to go to an extreme depth. So from a node, we are starting to explore a node. We are basically choose a node, and we are going to go to an extreme depth, right? But on BFS, it is kind of a different. We are going to go with the breadth. We are going to go on the breadth. But breadth, I mean, say, its level. It is going to go, we are going to go with the level by level. We are going to go with some level by level. How? So let's suppose this is my source. This is my source. This is my source. And from here we have to traverse. So from one, what all the opportunity we have to explore, which are, again, we similarly need a visited. There is no change on this. But now, as we are going to go to the level by level, so on BFS we need a queue. We need a queue data structure. So queue, you guys is should be aware of queue and stack data structure. If you're not aware, just quickly do a Google on yourself and make yourself familiar with the queue data structure, right? So from one, if I have two opportunities, then on DFS we are arbitrarily choosing one. We are arbitrarily choosing one, and we are going to go extreme depth of that particular node. We are from that node, we are again choosing an arbitrary and going to again go to the extreme node until we don't have the opportunity to further exploration. Until we don't have the opportunity to further exploration, we are going to extreme depth. We are going to go to the extreme depth. But on BFS we are not. From one, what are the opportunities we have? We have 2 and 5. We have 2 and 5. So now we are stating we will explore both on the same go. We are going to explore both on the same go. So on my next part, on my next go, we are going to explore both. We are going to explore both 2 and 5. We are going to explore both 2 and 5. I am going to write the pseudocode also on the same time. So when we are at node 1, we are going to mark the visited of 1 to be 1. So that means this particular node is visited. And we are pushing this particular node which we are doing the visitations to be our queue. To be our queue. To be our queue, right? And then we are running a while loop while my lane of queue, because until we have labels, we are running our queue. We are going to run our queue. And what is the number of nodes to this particular level? We are going to store them to be my lane of queue. So that many node we have to this particular level. So on the first level, if I am going to mark it to be 0 level, how many node we have? We have only a single node. On level 2, how many node we have? We have 2 and 5, 2 nodes. So what we will do, we are going to run a for loop for underscore in range nn. So that means we are going to explore all the nodes in this particular level. In this particular level, all the nodes we are going to check. We are going to pop this particular node from our queue. So we are popping, let's suppose 1. So queue dot pop left. So it is a dequeue eventually. We are popping our node from the queue and we are basically searching similarly for neighbor in graph of node. So when we are at 1, if I can make it on a single page. So when we are at 1, who are the neighbors? So for underscore in range nn, how many node we have? Nn is 1. Nn is here 1. So we are going to iterate one loop and we are popping 1 and we are going to iterate for neighbor in graph of node. So for 1, who are the neighbors? 2 and 5. And we are checking if same check. If I can zoom it little bit, same check. What is the check? If my visited of neighbor is equals to 0, so that means this node is not visited, then we are going to push those to my queue. We are going to push that neighbor, this is actually my neighbor, to be queue and marking this particular neighbor to be visited. We are going to mark this particular neighbor to be visited. Now if I again going to zoom out, so that is the algorithms. That is only the things that you have to write, and rest of the things is going to be taken care. How? Let's do a quick dry run. So for 1, we are popping 1 from here and we are iterating. So q.pop left, 1 has popped out here and we are running a for loop to all of its neighbor. Who are the neighbor? Are you guys able to see it? If not, then do a little zoom on it. Who are the neighbors? 2 and 5. 2 and 5. So we are going to check if that neighbor is not visited. Yes, 2 and 5 both are not visited. So we are going to mark both to be visited, and we have push both 2 and 5, right? Now for our next iterations, and 1 has popped out, right? We have popped out 1 initially, right? By this line we have popped out 1 and we have pushed 2 and 5. And now for my next iterations, what is the nn? Nn is come out to be 2, and we are running a for loop of size 2, and from 2 we are checking which node we can explore. From 2 we have only single opportunity, we can explore only 3, which is unvisited. So we are pushing, so we have popped out 2. So our queue has only 5 on it when we are at this particular junctions. Right? When we are at this particular junctions, we have popped out 2 and we are checking who are the neighbors which are unvisited. Which one is those? Only 3. We have pushed this 3 to my queue. Then again the for loop, we have iterations count of 2. Right? We have iterations count of 2 because we have on the last levels we have 2 and 5, two nodes, right? We have 2 and 5, two nodes, right? So again we have popped out 5, and for 5, what is the opportunity? We can explore 4, we can explore 4, which is unvisited. So go for it, go for it. So we are pushing 4 also, 4 also, right? So two iterations done, two iterations done. Do we have any other? Do we have any other? Nope, nope. That is the only explorations we can do for this particular node. So see guys, see guys. So for next levels, all the nodes, for next levels, all the nodes, what are the nodes of the next level? From 1, from 1, in one distance, 1 unit of distance, we have 2 and 5. We are simultaneously pushing 2 and 5 in our queue and popping simultaneously 2 and 5 from our queue. And when we have 3 and 4 to our queue, so that means on that particular level we have 3 and 4. What is the base? From 0, from this one node. So from one node at a distance of unit 2, we have two nodes. Who are those? 3 and 4. And you can see guys, currently we have 3 and 4 in our queue. At 1 unit distance, we have 2 and 5. Similar game you can perform from here. From 3, we don't have any explorations. 3 has popped out. From 4, do we have any opportunity? Yes, yes, yes. 7 we can explore. 7 you can explore. So you have just pushed 7. So for next levels, so that means next level means what? Next level means what? As considering base at 1, considering base at 1 at a distance of 3 unit, we have only node 7. We have only node 7. So that is actually mean by this particular node 7. So for 7 we have popped out 7 on next iterations. And do we have any further opportunity? Nope, nope, nope. And our BFS is going to be end. Our queue is going to be empty. So you guys is understood, right? What is the fundamental difference of the BFS and DFS? If not, then that is the ideal times. You guys can ask one time, twice, thrice. I am bound to give you the answer on any part. If it is not clear, then please feel to ask on that particular time. But I am assuming the way that I have explained that in depth with the dry runs that we have explained, there should not be any doubt. But if you have on DFS also, if you have any doubt, please clarify now itself. Please clarify now itself. So the main fundamental difference of BFS and DFS, if I can going to write again a graph. So the main fundamental difference of the BFS and DFS is for DFS we are, if I am from 1, if I am starting to explore these particular directions, then I am going to go to the extreme depth until we don't have the opportunity to explorations. We are going to go to the extreme depth. We have done the entire path explorations, then we are going to go to this particular path. But for BFS, we are going to go with the level by level. For 1 unit distance, who are those? 2, 5. Next level, who are those? 3, 6. Level complete. All maximum levels from 1 we have explored. From 1, all maximum levels we have explored. So that is the BFS. So this is the fundamental difference of BFS and DFS. One is going to extreme depth. That's why it is known as depth first search. And another one is going to go to the breadth by breadth, level by level. So that's why BFS is also known as level order traversal. So if anyone is asked you or on an interview, if someone has asked you to write the level order traversal, so by blind eye you can write the BFS. So they are basically looking for breadth first search, level order traversal or breadth first search traversal. Both are same. Clear, right guys? It's clear. Please provide a thumbs up. Please provide a GTG good to go. Please provide a good to go so that I can understand. Till this point we have covered 3 things: type of graph, representation of graph and traversal of graph. So this is the foundation. This is the fundamental or the foundational part. If these things is clear, then you should be like able to solve more than 60 to 70% problems. Few problems are basically rely on a predefined algo, eventually discussed, but that algorithm is also based on a graph traversal algorithm. That algorithm is also based on the graph traversal algorithm. So graph traversal algorithm is the must you have to understand. This BFS and DFS is the foundation of any algorithm, any algorithm. So that's why I am repeatedly stating, guys, if you have any doubt, please feel free to ask right away. Please feel free to ask right away. Or else, please give a thumbs up or a GTG in the chat. In the chat, please give a GTG in the chat, that if you are good, if you are good, then please give a GTG on the chat. Okay, okay, I got one GTG. You have understood, I am very glad. Anyone else, anyone else who are in the who are in the watching list, please provide a GTG or a thumbs up. Okay, okay, another GTG. Okay, nice, nice. Clear, right, guys? So with this note, can we jump to a solve a particular problem? Can we jump to solve a problem directly from our sheet, which is actually asked on a multiple product based company? Can we go? Can we make a try? Can we make a try? Let's try. So the problems that we are going to try to solve is the number of island. It is based on the graph traversal algorithms. If you understand BFS DFS very in depth, you should be able to write on your own. So take your time to just quickly iterate to the problem statement. Just quickly iterate to the problem statement. I am putting a 2 to 3 minutes timer. You guys go to the problem statement on your own, try to understand, try to code it also, and post that we all eventually do the codings together. So but before of that I will highly encourage to you guys to go to the problem statement, understand the gist, and try to map to the algorithms that we just understand, BFS or DFS. Try to solve it, either of them. Try to solve it, either of them, right? Just make a try, guys. I will just going to come back in 2 minutes, 2 to 3 minutes. Just make a try, just make a try. The cheat sheet is already shared in the video description. On video descriptions you can find the DSA cheat sheet, and on that cheat sheet you can search on the graph topic. So I'm just going to give you how you can navigate the problems. You can go to this graph, and on the graph you can see the URL here. This is the problem URL. You can just copy this URL and paste it to your favorite browser, and you will going to see this screen. Just do that and you are able to access the problem, right? Yeah, just make a try. I am going to come back in 2 to 3 minutes. Very shortly, I am going to come back. Just try to make a try on your own, or at least understand the problem statement. Okay, hi guys, hello, I'm back. Just quickly confirm audio is clear, right? I hope so. I have just deactivated that and I have reactivated it back, so it should be okay. Fine. So I'm assuming you guys have already went through. You have already went through the problem statement, right? So can you guys just quickly type on the chat, like on BFS and DFS, which one is which of the algorithm we have to apply here out of BFS and DFS? We definitely need a graph traversal algorithm. That's the for sure that you guys are all agree. But can you just quickly type which graph traversal algorithm is going to work here? It's BFS or DFS. Which one is going to work here? BFS or DFS? Anyone? Any guess? Any guess? I'm fine with any wild guess also. But just type here on BFS and DFS which one is going to work here. No one. No one can just tell me the algo. Okay. BFS, BFS. Okay. Okay, nice. Okay. So we have couple of answers. BFS is right and DFS also are right. So ideally, these problems can be solved by both BFS and DFS. And I think this is an ideal problem where we can practice both our learnings, which is both BFS and DFS we have learned, and let's try to solve it with both BFS and DFS, right? Okay. So the constant is very small, that is our m and n can be 300, so our maximum grid size can be 300 cross 300, that is 9 into 10 raised to the power 4, right? So with this note, let's start to solve it. So first I will try to solve it with BFS and then I will solve it with DFS. Okay. So I have defined my n and m. So n is the number of rows and m is the number of columns I have, right? So this we need. Then what else we need? What else we need? We need a visited. So visited I can define this as a default dict of int. I can define it. Agree? We can define it as a default dict of int. Then what we need? We need a queue for BFS. We need a queue for BFS. Till now, good. We have just done the definitions of the things or variables that we need, right? Then what we can do, given islands, or now we have to tell them how many island is there. And then what we need an answer for sure. We need an answer for sure. Answer we can start it with 0. Now we can start our function call. We can iterate for I in range in, for j in range m, right? Then we can, so I am making everything's inside a function only, so that you can reuse this particular template for other purposes also. So I am passing x and y, so this is my node. And what actually my BFS should be looks like, so visited I have to define on outer side. 2 I can get rid of from here, because I am making it to a function scope. So I can make my q to be, this is my definitions, this is my caller, this is my actual BFS. So my q should be, q is a dq we can take. Then we are marking my v's of whom, v's of x and y, that is the caller to be 1, and we can push to be our, on our q to be q dot append x comma y, right? Whomever we are lying, we are pushing this to the q. Then we are exploring, while my lane of q, we have something n to be my lane of q. Then for underscore in range, see guys, how familiar with I am with my template. See how fast I am going to write. I don't have to think about what I am writing. So that level of speed, that level of clarity, you have to gain to crack any top product company. That level of clarity you have to gain. So that is how I am going to get that clarifications, how I'm going to get that confidence. That is only by rigorous practice. There is no shortcuts, there is no shortcut, there is nothing at all. I am going to give you the templates, but the template is also going to be a stagnant things. Until you do a rigorous practice, you are not going to apply the template to the problem. So to apply the template to the problems, you have to do a rigorous practice. So now I am popping whom, let's suppose I am popping my, I am marking it to be xxyy to be q dot pop left. I have popped those, and then I am going to go to the all of its neighbor, but in the graph. So again, that is a very good problem guys. So on this, you have grid versions of the graph also. You are solving a grid versions of the graph. So for the grid versions of the graph, I have another like very sweet neighbor identifications. So see it guys, see it. So for neighbor, so neighbor is my dx dy, actually my neighbor in range. Whatever the directions we have four directions, right? Adjacent lands are horizontally and vertically. So we have four directions: up, down, left, right. So let me just quickly define those. So for I in, I am going to define 0 1 1 0 minus 1 0, then 0 minus 1. So this is my four direction movement. So what the first things I have to check? My 0 less than equals to x plus dx, sorry, it is xx plus dx less than n, and 0 less than equals to yy plus dy, right, less than m, and v's of whom, v's of xx plus dx comma yy plus dy equals to 0. So that should not be visited. And when I am going to make a call, when I can going to jump on that particular cell, when it is a land, so my grid of xx plus dx yy plus dy is equals to 1. So this is a string 1, right? Take a note guys, this is a string 1. I actually like take a hell lot of times to basically figure out why it is going to get a wrong answer, why I use solved on past. So it is a string 1, just take a note. If it is so, can I push it to my queue? Yes man, you are definitely going to push it. Xx plus dx, then yy plus dy, and then I am going to mark it to be also to my queue xx plus dx and yy plus dy to be a visited one. right. So I am going to this particular cells, I am going to spread entirely to be visit all, to be visit all. Then, and when I'm going to make a call to my helper functions altogether, if my v is off, tell me guys, v is off, here I have I and j is equals to 0, so that means it's unvisited. So we have find a disconnected component, disconnected land, and from that we have to try to explore, we have to try to explore all the adjacent lands, from that to all the adjacent lands, from those to all the adjacent lands, until I am not able to explore any further lands. That spreading we have to do, that spreading we have to do. So that means it is an unvisited, and it is a land, it is a land for sure, and my grid of ij should be equals to 1. So if it is a land, if it is a land, and if it is an unvisited, so start your BFS to spread the landing to check how far it's unvisited, how far it's unvisited, and we have land, how far it is unvisited and its land. Make it all to be visited in the same go and mark it to be a single component. And I am making a call on this to my helper function with this ij, and I know when I'm going to make a call to my helper function, it is going to take care of all of its, all of that particular segment, all of the particular segment of land visitations, all of that particular segment land segment visitations. And I am going to mark my helper ij, I am going to make a call, and I am going to take my answer to be plus equals to 1. So I have found one segment of answer, right? That's it mostly. And if I'm going to return my answer, it should work, it should work. Let me make a try. Okay, it is giving correct answer to the sample test case. Let's try to make a submit, let's try to make a submit. Hopefully so, hopefully so. Yes, we did it. We solved our very first graph problems, which actually asked in top product based companies like Google, Microsoft, Amazon. This kind of company has asked this particular problems, number of islands, and we have solved in life, we have solved these problems in life, we have solved these problems in life. Any doubt, we have solved it in BFS versions. The BFS versions is the harder one of it, the harder one of it. The DFS is going to be the little simpler one, I have to say. But we have solved it, but we have solved it with its BFS version only. Clear? Any doubt on the BFS versions? If not, then we are going to jump on the DFS versions. Quickly on the chat. If it's clear, then please guys provide some like on the stream, right? If you are going to get anything, if it is going to help you at least 1 to 2% at least to your preparation journey, then please provide a like, and please subscribe guys. Please do a subscribe also. That going to help you, help basically make myself more motivated to make such videos. Please provide a subscribe, please provide a like. Right, so I assume it's clear. We did the live coding. I have explained every line, why I am writing those, what is the backbone of using those, right? Okay, so I am assuming the BFS versions is clear to all of you. So with this, we can try of its DFS version. So DFS versions is going to be a little easy ones, I have to say, for this particular problem. So now see how much changes I am going to do. So this helper should be helper. I take one more functions def helper. I am going to call it to be helper DFS, and I am going to take same arguments x and y, right? I am going to basically create a new function altogether. I am not going to use this helper functions, because on this helper functions we have solved it with BFS. Now I am going to use the helper DFS, and if I am not going to make any call to my helper this function, then it is eventually a DFS based solution. See guys, the changes that I am going to do on this particular problem to make it on the DFS version. See, we do the same things. V's of my x and y to be visited. Neighbor exploration, same things, nothing fancy. Copy, I have copied the same lines. Not this line, let's copy this line also. There is no change on these lines. We have to explore our neighbors, and neighbor explorations is going to be same only. Make the indentation corrected. Now we don't have x, we have only x, y, we have x, we have y, here we have x, we have y, and if it is so, then we are going to make a call to be x plus dx, y plus dy. That's it. Should work, right? Should work. Now I'm going to make a call rather than my helper to my helper of DFS. That's it. This few lines should work. This helper is a dead code only, because I am not going to make any call to this function. Sorry, my bad. So this should be my helper of DFS. This we can comment also. Let's make a done. Then I can do run full. Yes, it is giving correct answer only. So just for your clarity, I have entirely commented the BFS versions and I am rerunning. So yes, it is giving correct answer. Let's make a submit. With the DFS versions. Yes, it's indeed accepted. See how quickly I toggle my BFS versions to be DFS versions. Less than 2 to 3 minutes. 2 to 3 minutes for sure. Less than 2 to 3 minutes. I'm damn sure. Less than 2 to 3 minutes. Just see which lines, which tweak just I did, and it's going to convert it to the DFS version. So that's why guys, I was repeatedly focusing on the dry run explanation part of this BFS and DFS, because that is the backbone. If this fundamental things is clear to you, then these things are just a cakewalk. These things, writing the code is the cakewalk. There is no super magic, there is nothing on this. It's a very standard cakewalk. And when you are solving a good number of problems, no guys, then to have this particular template set to your blood level, so you are never going to think which lines I have to write first. Do I have to define my visited here? Do I have to define my visited to be class level, method level? When I have to push the things to my queue, when I have to, these things you are never going to be thought of before writing a single line. You are just going to know this is my template, done. You are going to get a accepted on just like 2 to 3 minutes. See how fast I change the template, how fast I change the BFS template to the DFS versions. Less than 2 to 3 minutes for sure, right? So we have solved one of the most asked problems, number of islands, with two versions. One is the BFS versions and another one is the DFS versions, right? Okay, fine. With this we can move to our next problems. The next problems is the clone graph. clone graph. Okay, so let's try to understand the problem statement first. So on problem statement understanding, I am again going to give you guys 5 minutes. So it's now 20:58. I am going to come back with 9:05. 9:05 I am going to back. Just read the problem statement, clone graph, how you can access DSA sheet. The DSA practice sheet is already attached in the video description. On this, go to the second graph problem, which is clone graph. And on the clone graph, you can copy this link and paste it on your favorite browser and you can going to access it. You are able to access it. Fine, just read the problem statement. I am going to come back by 9:05, sharp within 9:05. Okay, I think guys, you guys have already went through the problem statement. If not, then let's just quickly do together. We can go to the problem statement together because we are running a little late of time. Let's try to solve another 1 to 2 problems. Yeah, so on this problem statement, it is very simple. They have given a reference of a connected undirected graph. You guys should be already aware of a undirected graph, what it is. It is connected. Connected means, so on the last problems you saw, right? It is an undirected. It is a disconnected graph. So on that, the lands basically, a chunk of lands is basically a part of a single connected component. So we have to find the number of components, number of connected components on that graph. So, but this graph is altogether connected. There is no separate graph segment. By that they have tried to basically mention that. So it is a connected undirected graph. Now we have to return a deep copy of the graph. Each node in the graph contains an int, which is a Sorry, can you guys confirm you are able to see my perfect screen, right? Sorry, I was basically showing some another screen. You are able to see, right? Sorry, my bad. I was actually on a different screen. Okay, fine, fine. Okay. So, on this, the graph contains an value int and the adjacency list. So, the adjacency list is the neighbor of it. So, class node, this is the node of the graph, and it has a value of val and a list of type node who are its neighbor. Now, on this you can see, for simplicity, each node's value is the same as the node index, one indexed. So for example, the first node value is val equals to 1. The second node value is val equals to 2. So this means whatever the value it is giving you. So if you are at node 1, so val basically stands for its value actually. So val equals to its actually node number. So val1 is the node number of that particular node. Similarly, the second node is val equals to 2 and so on. The graph is represented in the test case using an adjacency list. This is represented as an adjacency list. So that's the reasons I was initially stating this. Adjacency list is the most common format of representations of the graph. An adjacency list is a collection of unordered list used to represent blah blah blah. I think we have already discussed how adjacency list should be looks like. The given node will always be the first node with val equals to 1, the given node. So you can see on this they have given us a node with, so inside this node we have this val and neighbors, and this val is equals to 1. The val is equals to 1. So that they have make sure this value is 1. You must return the copy of the given node as the reference of the clone graph. So you can see the input is self, then node of optional node, and we have to return the same of data type optional node. So we just have to create a clone of this particular graph, right? It is very straightforward problems on my opinion. So the input you can see it's a kind of it's a adjacency list representations. So for this is the first index, right? We can number this 1, 2, 3 and 4. So for 1 we have two connections. Who are those? 2 and 4. 2 and 4. So here you can see from 1 we have 2 and 4. For 2 we have 1 and 3. For 2 we have 1 and 3. From 3 we have 2 and 4. From 3 we have 2 and 4. And from 4 we have 1 and 3. From 4 we have 1 and 3. See? So it's clear, right? The representation part is clear. And we have to return the same thing, same clone of a deep copy of this particular graph. There is no super magic we have to do. They have given us the graph. We have to return the same graph with a copy of it. The node pointer should be a new node pointer. That should not be a like given node pointer. That should be a deep copy or a new copy of the node pointers, and with this we have formulate the graph and we have to return it. That's the problem. That is the problem. So let's try to code it. Let's try to quickly code it. So what do we have here? So we have this adjacency list to be not in the form of adjacency list. Do we have it in the form of adjacency list? No, we don't have. It's kind of a node to node linked. So they have given the node 1's node pointer, and from that we have to jump on the neighbors and we have to define our graph. So let's try to first define our graph very quickly. So our graph to be a default dict of int, right? no, sorry, not a default dict of int, it should be a default dict of list, adjacency list. Now what we can do, tell me guys. We can start def helper. Let's try to solve it with a DFS. If we are good with this, let's call with a node. Then what we need, we need a visited for sure. Any graph traversal algorithm, we need a visited array for sure, visited list, visited array, whatever you want, you can take it. Let's take it as a again default dict of int. Clear. Mark v's of whom? Node of val. Where the val is stored? Node dot val. Node dot val. Mark it to be 1. Clear. And we are going to make of graph of node of val. We can initialize to be an empty list, and we are iterating. For neighbor in graph of whom? Graph of, so we don't have the graph, sorry, my bad. So who are the neighbors? It is of node dot neighbors. This is my node dot neighbors, right? And we are going to check. What we are going to check? We are basically, we can link it to for sure. So graph of node dot val dot append. We can append whom? We can append neighbor dot val. So that is the neighbor. And as it is an undirected graph, we have to add back the edge from neighbor to node also. Neighbor dot val should be my node dot val. So we have connected both by both. So that is actually mean by undirected graph. And then what I am doing, marking to be making a call if my v's of whom? Neighbor dot val, right, is equals to 0. So my neighbor is not exposed yet. Let's expose him. Helper of neighbor. So with this, I am just quickly printing my graph to see if it is correctly formed or not. And for current purpose, let's return a none. We are just going to debug it quickly. Just quickly debug it if it is perfectly formed or not. So we have whom we are printing. Okay, we didn't make a call to the helper functions. Then how it is going to be formed? My bad. Make a call to helper of node. Try to see it. Let's see it. What is the issue? V's of has no attribute val. We are passing no type. What is the issue? Node dot val to be 1, and it don't has any attribute of type value. Okay, my node can be, what is the constraint? The number of nodes in the graph is range of the 0. Okay, it can be 0 also. Okay, so we can add a basic validations. If my node is none, or we can say not node, so that means my node is none, then we don't have to do anything. We can do these things. So my node can be none also. Okay, so for 1 we have couple of pushes. Wait, so we have 2 2 and 4 4, 3 3 and 4 4. Why we have 2 pushes? For okay, we don't need, right? Because when we are at 1, we are going to push to 2, and when we are at 2, then on that times we are going to push 1, right? on my graph, when we are at 1, we are marking 2 also, and on 2, when we are at 2, we are again going to mark it back, so we don't have to do the binary marking on these particular positions. That is going to be taken care by this. And on 2, we have to make sure we are not going to visit 1 again, so that is going to be taken care by these below conditions. But from 1 to 2, the time of marking, we don't have to mark 2 to 1, because when we are at 2, then on the for loop iterations of 2, it is going to be handled. So let's see if the graph adjacency list formation is correct or not, because that is the foundation. See, it's correct now. For 1, we have 2, 4. For 2, we have 1, 3. For 3, we have 2, 4. For 4, we have 1, 3. Clear? It's clear, right, guys? Clear? Perfectly clear. Now, go forward, move forward. Now, let's define our answer to be a, what we can define? We can define as a dictionary. Now, do the starting. Now do the new clone graph preparation. So how many node we have? The length of my graph. Let's store it also to be some variable. That many node we have. My lane of graph. Then iterate for I in range whom nn. I am iterating, right? For I in range nn, I am iterating, and I am going to create a node of it. Graph of on answer graph. What we are actually looking for? We have to create a new node out of it. So answer of I should be a node. How we can create a new node? By stating it node. And what is the val of it? Can I say it should be 1 to nn plus 1, because it is numbered from one index based. Here it is mentioned it's one index based. It's not from 0 to n minus 1. It's from 1 to n. So we are going to make a call to be of I. Answer of I to be node of I. We have made a call. Answer of I equals to node of I. Then what else? I think we are good with the val. We have created new node and we have assigned successfully the val part, but the neighbor part is still pending. We have to also set its neighbor correctly. So with the answer of I, we have just pointed the correct new nodes with the correct val, but never initializations, never assignment is still pending. So let's do again for I in range 1 to nn plus 1, right? 1 to nn plus 1. Now for 1, who are the neighbors? 2 and 4. How we can get the 2 and 4? We can iterate 2 for neighbor in graph of I. So graph of 1 will give me the neighbors. So this will give me 2 and 4, right? So on neighbor we got 2 and 4, and we can take a LL to be a list, because you can see my neighbor to be a list of node. So my neighbors can be whom? Tell me. I can do ll.append on my neighbors list. I can append whom? I can append answer of neighbor. When we are going to call, we are going to get the neighbor list. We can going to get the neighbor new node that we have formed here. We are going to get the neighbor new node and pushing it to my LL and finally when we are done with my LL preparations, can I say my answer of I of my neighbors should be whom? Tell me quickly, tell me guys. It's nothing but my LL. And we can return the same format. They have given Node of 1 they have given, we can also give them answer of 1. We can also give them answer of 1. Same things we can give them. Quick run, quick run. Yes, yes. All sample test case passing. Quick submit, quick submit. Finger cross. It should going to get accepted. Yes, it's indeed. It's indeed. Done and dusted, guys. We have solved two industry levels, not on the industry level, it's beyond industry levels for sure. Two medium problems we have solved on graph, which are actually asked in top product based companies. We have solved couple of them in live, couple of them in live. Clear? Clear? Things is very clear, crystal clear to all of you. I am hoping so. I am hoping so. Things are very clear. I am assuming it should be. It should be. It's clear, right? Anyone on the chat? Anyone on the chat? We have solved two industry standard problems. First one we have solved on both BFS and DFS, and the second one we have solved on this particular things with DFS. With DFS we have solved the second one, and it should be very crystal clear to you. Any doubt, any question, please feel to ask right away. Please feel free to ask right away. Okay, okay, okay. I think you guys are getting it on the very good note. Okay, now let me quickly check the time. Okay, it's 21:20. We are almost 2 hours over. I'm thinking like, do we have to solve one more new problems, or we can stop, or we can take it for tomorrow? We can do a live tomorrow also, guys. Like if you guys are all fine, then we can take a live on tomorrow, because today I think it's too late. It's kind of a like 9:30, 9:30, and the next problems is again going to course schedule, and this problems is again, so every problems on this particular sheet is going to associated with a new topic. So this every problems is going to take a little bit time to basically explain and giving you the explanations, and also you guys also need some time to digest, because on this course schedule we have to learn a new concept of cycle detection algorithm in a directed graph. So that is a topological sort. So these things we have to learn. So this is completely a new topic, and this will take a for sure and like 15 to 20 minutes, and then coding it another 10. And so this is seems to be an half an hour work if we are going to pick it, because this is not going to solve a very standard BFS and DFS. There is some different things that you have to know. So that's the reasons, guys, I am stating, if you are aware of all the algorithms of the graph, then graph is the very most simple, most easiest data structure, or on the algorithm parts, I have to say, if you know the algorithms. But if you don't know, then this is the most toughest part of over all the data structure and algo, right? So I think today we can stop here. Maybe from tomorrow we can take another 2 to 3 problems, because all the problems listed on this particular sheet are on the next level problems, and this actually needs some good amount time to explain to you and give the gist to you guys before we can start on the problem statement. Because course schedule, the next problems that I am stating, it's again a new topic altogether. So better if we can stop here. But again, I am giving you the responsibility to you guys. If you guys are all okay, then we can stop here, and you guys can take your time to digest this BFS, DFS, and the theory part that we did, and on the tomorrow we can uh, resume from this particular point, right? If you guys all good here, then we can do that, then we can do it, or we can continue today. Just give it a shot, like we can take today or tomorrow. Anyone? Okay, I got one response. Tomorrow, sir. Today is fine. Okay. But okay. So I am also thinking on the same note. Let's digest what we have learned so far on today's topic. We have understood two backbone pillar of graph, that is graph traversal algorithms, and few foundational things that we have to know. So this part we have covered, and we have covered BFS and DFS very in depth. So let's digest this part first and solve couple of 1 to 2 more problems of BFS and DFS based. Then from tomorrow onwards we can continue on the next problem sets that we have. Right, so I am here another 2 to 3 minutes to you guys. If you guys have any doubt, any problems, any QA that you have on your top of your mind, then you can ask it now. I am happy to answer you if you have anything, or we can just 2 to 3 minutes we can cut the stream. We can cut the stream. So I am going to go to be on the ending screen, but I am here with you. If you have anything, you can feel free to ask, or by 21:30, that is 9:30, stop the we are going to stop the uh, streaming. We are going to stop the streaming by 21:30. I am with you guys another 4 to 5 minutes. Just feel free to ask anything if you have top of your mind. I'm going I'm going to answer those in the chat very quickly.